Okay, so let's try the next coding exercise. So open the leetcode.com and go to the problems tab and search the question number 2385 and hit enter. So we have the question number 2385, amount of time for a binary tree to be infected, and it's come in the medium category. So let's click on it. So we will try to solve this question. All right. So let's read the question, like what the question is says. We need to find the amount of time for a binary tree to be affected. So this is a tree question, right? And we need to find some time. So the output should be some time. Okay. You are given the root of a binary tree. So we have root is given, which is perfectly fine. So if the tree is given, then the root will be given. Along with that, root of a binary tree given with the unique value. So all the values are unique. So let's suppose there is a one, so one can't be repeated. If the three can't be repeated. Okay. And we have a one integer is given start. So we let's suppose there is a function. We have the root is given. We have some integer is given start. Okay. A minute at minute zero. At minute zero, an infection starts from the node with value start. So let's suppose there is a tree, and this 3 is the start node, and this is the infected node. So at the 0th index, this infection gets started. So, and this infection gets spread across all the tree, and we need to find out how much time it will take to spread across all the tree. So let's jump into the whiteboard. So let's suppose this is a tree. So you could see this tree. This tree is given, this tree. So you could see all are the green nodes which are healthy, and one is the red node which is unhealthy. So this is the infected node, right? So this 3 is connected with 1. This 3 is that, like, the neighbor node is 1, the neighbor node is 10, the neighbor node is 6. So at the first second or the first minute, it is going to affect this node, one node, right? Within the 1 minute, it is going to expect this. Within the 1 minute, it is going to affect this, and within the 1 minute, it is going to affect this as well. So till out of like this like 4 and 4 8 nodes, within 1 minute 4 nodes has been affected. Now once the node number 1 has been affected, in the next minute it will affect the nearest node, the neighbor node. So one more minute. So 1 minute here and 1 minute here, so total 2 minutes. Now once the node number 5 got affected, it's going to affect node number 4, so total 3. So till here 2. So once the node number 4 got affected, the node number 9 and node number 2 will be got affected within the same time, that is the 4. You can say the 4 minute or the 4 second. So the output should be 4. So we need to find out the maximum time. All right. So we need to find out the amount of time, the how much time it will take basically to affect all the nodes. Okay. So this is the problem. Now how we are going to solve this? So let's try to see, like, if we, let's suppose if we don't know any algorithm, we don't know anything, just by looking into this problem, what's come into our mind? So we know this node is given, this is infected, and we know in the tree we know how to traverse to right and how to traverse to left. All right, if we do node dot left and if we do node dot right, then we can easily load. So let's suppose we are on the node number 3. If we know, like node dot left and node dot right, we know already. So we can easily reach node number 10 and node number 6. And if there are few more nodes after 10, then we can also easily reach. So there is no challenge, we can easily reach. But the challenge is how, because this is the infection. Infection is traversing the parent as well. That is infection will be on the parent as well. But in the tree, how we are going to traverse opposite? Like, so that is a little challenge, right? So because tree has two pointer, left and right. So left is 10 and the right is 6. But tree doesn't have any pointer for the parent. So how it's going to go above? Then how we are going to traverse to above? Because until unless if we not go above, then how we are going to traverse this area, right? So this is the challenge. So if we crack this challenge, then then this question is very easy. Then to write the code is just a like very basic thing. Okay, so let's try to crack that thing. So what we can do is we will treat this tree as a graph, because in a tree we can traverse only left and right, because if we add the node 1 then we can go 5 and then 3, and on the 3 we can go only on 10 and 6, but we can't go from 3 to 1. But if it is a graph is a connected, so tree is a form of a graph as well, but if it is a graph there is a no directional. If there is no directed graph, then we can like go from 3 to 1 as well, then we can treat it as a graph. So for the graph, we need some metrics, adjacency metrics. So basically, what we can do is we will create a dictionary. We will create a dictionary which contains which node has been connected with all the other nodes. So if we create this dictionary now, then our work is almost done. So let's suppose we are on the first node, because we know the root node is given. The root node is given. So we are on the first node. Okay, we will create a dictionary. Okay, 1 is connected with 5 and 3, which is fine. Then 5 is connected with 4 and 1. Then 3 is connected with 1, 10, and 6. 4 is connected with 5, 9, and 2. 10 is connected with 3. 6 is connected with 3. Like connected means basically the like a neighbor node, because if you consider from the tree perspective, then 10 is not connected with 3, but if you consider from the neighbor perspective, then 10 has the neighbor 3, because I said like we will treat it as a graph. So 10 has 3, so 6 has 3, 9 has 4, 2 has 4. So we will create this matrix. So now the challenge is, because this is a tree, we have only one pointer. So 5 and 4. Then how like, okay, for the 1, 5 and 3 is easy, because as soon as we are on the root node, we can say okay 5 and 3. For the 5 we can put 4, but how we are going to put 1? So what we will do is, as soon as we know our left node is 5, then what we can do is we will make it as a key as well, and we will put value as a 1 as well. So first let's jump into the code, and let's try to create this adjacency matrix only, because this is the first step. Until unless we don't know the neighbors, then how we are going to calculate the time, how much time it is going to take to get infected across all the trees. So first we are going to create the adjacency matrix. So this is a dictionary, right? So let's create a dictionary. So we have the dictionary adjacency matrix. So you can create a dictionary like this, or what we can do is, because this dictionary is further contain the list, right? So this dictionary contains a list. So what we can do is we can create a default dictionary which contains the list. Like why I am doing this is, even like there is no need, you can directly do like this only, a normal dictionary. But there is a little more code if you do like this, because before inserting you have to check if the key exists. If it doesn't exist, then you have to give the default key as a dictionary. So that's why we are taking as a default dictionary. So we will import this. So from collections, import default dict. Okay, so this is normal, like we just created a empty dictionary. Now the challenge is we have to create this. So what we can do is, like we have to traverse the whole tree to find the node. So how we are going to traverse the tree, either using the BFS or the DFS method, or BFS or DFS method, and whatever the you are going to use, you have to use either queue or either stack, because first you are on the one, and then you have to store 5 and 3, then you are on the 5, then 4, then 3, then 10 and 6, right? So the same thing we are going to do. So let's take a queue. Let's take a queue, and in the queue, what we can do is, in starting we are going to insert our root node, right? Our root node is given. Right? And if you see the constant, the number of nodes in the range lies from 1 to 10 to power 5. So there should be at least one node. So we don't need to check whether the root node is empty or not. We don't need to check. Correct. So first in the queue, we are going to insert the root node. Now, because till now we are just creating a dictionary. So in the queue, we have this. Right now we are just going to run the loop. We will pop this and let's try to do this. Now what we can do while q. Okay, now we are going to pop q dot pop. Okay, now we are popping this. Now what next? Now we pop this. So once we pop this, what we can do is we will check if this has, let's suppose if there is a one element only, if there is a one element, then there is a no left child, then there is no right child, then there is no adjacency matrix dictionary, right? So we will check if node has left child or not. So if node dot left, so if there is a left child, then what we can do is we will create a adjacency matrix for one, and in that one we are going to insert 5. So adjacency matrix, right? And the node is node node dot value, because we are taking the value only, and the value means like this is a tree. So how we are going to catch the value? Value means one, because we need to one here, one, right? So we put one here. Now dot append, because by default we have the dictionary, we have the list, the value as a list. Now in the list we have to append something. What we have to append? 5. So what we have to append? Node dot left dot value. What we have to append? Node dot left dot value, which is fine. Now, and we will check if node dot right, then we will also do approximately same thing, node dot value and node dot right dot value. So for the one we have inserted 5 and 3, right? So for the one we have inserted 5 and 3. Okay, what next? But if we just do only this thing now, and so in the queue we have this. Now the while loop will run again. Now it is going to pop 5. Now it is going to pop 5. Then for the 5 it is going to attach 4 only. It is not going to attach 1, because for the 5 we are again checking if it is a left child. No, there are no left child. No, there are no left child. It has a right child. Yes, it has a right child. So 4. So it is going to set 4, but we need 1 as well. So what we are going to do is, let me rub this. Let me rub this so that screen is clear. Okay. Now what we can do is, because here we already have the left child. Here we already have the left child. We have the left child and we know its node as well. We will just do opposite. So adjacency matrix. So instead of node dot value, what we will do? Node dot left dot value, and here append should be node dot value. That is the vice versa. Similarly here. So node dot right dot value is equal to node dot value. That's it. Basically we are on the first node, so for the one we put 5, but if we for one we put 5, for 5 we can put also 1 now. So 5 we can also put 1. So in this way we can create a whole adjacency matrix. So that's it. So let's try to first print it. Print adjacency matrix, whether this matrix is corrected or not. I know this solution is not complete, just try to run it, whether our adjacency matrix is like complete or not. So adjacency matrix spelling is wrong. So adjacency matrix, it should be matrix. Okay, let's try to run it. Okay, so something is wrong. What is none is not valid for expected return type integer. Type array string plus is not valid for the expected type integers. So during handling exception. So for 1 we have 5 3. For 5 we have 1. For 3 we have 1. So for 1 we have 5 3. For 5 we have 1. What 4? Okay, got it. We are not inserting in the queue. If the node dot left, we need to insert, because otherwise how we are going to pop? q dot append node dot left. Similarly, q dot append node dot right. So let's try to run it. Okay, so still some none is okay, leave that. But our let's see whether our like matrix has been created or not. So one has 5 3, one has 5 3, 5 has 1 4, 3 has 1 2 6, 3 has 1 2 6, 5 has what is this? 4 has 592, 4 has 592, 10 has 3, 6 has 3, 9 has 4, 2 has 4. So our matrix has been created, which is perfectly fine. This is okay, fine, because like they said we want integer, but you are returning none, which is fine because we have not completed our solution yet. So our matrix has been created. Now it's very easy for us. Now it's very easy. So this matrix has been created. Now we know for 3 we can easily traverse. Now we know. So what we can do is, because now we know for 3 we have 1, for 3 we have 10, for 6 now for 1 we have 5 3. So we can easily solve this. So urgency matrix has been created. Now what we can do is, we will take another queue. We will take another queue. Let's take a queue. And because we have to start from here, because this is the infected node, this is the infected node, we have to start from here. And for this node, if only one node is infected, the time is 0, because they said at time 0 the infection start. So if on 3 it is 0, then if it go on 1, then the time is 1 minute at minute. So it is 0 minute at it is 1 minute. So what we can do is, in the queue, what we can do is, we will take a start node. Start node is 3, and we will take a time. We will take a time is 0 second. 0 second, or you can say minute. Now we can run a while loop. While queue. While queue. Okay, so now in the queue, we put 3 and 0, because we have to start from the infected node, which is 3 and 0. So we put 3 and 0. Now we can pop it. We can pop it. Just pop it, 3 and 0. Okay, let's pop it. So node and time. So node and time. So q dot pop. So we have pop it. Now we have 3. So from the queue we get the 3. Now we have 3. So for 3, let's check the neighbor. Then how we are going to check the neighbor? From this urgency matrix we can check the neighbor. Okay. Now neighbor in for neighbor in this matrix, adjacency matrix of node, because it's a dictionary, so we can access the value node. Node means 3, because in the starting we have 3, so no adjacency matrix of node 3. Okay, so we have 3. So we get this value 1 10 and 6. So let's append everything into the queue. So we will append 1, we will append 10, we will append 6, but along with 0 we are going to increase the time by 1 because now we are inserting from 3 to 1, 10 to 6. So time will be 1 minute, 1 minute and 1 minute. All right, so what we can do is q dot append. So what we need to append, neighbor comma time plus 1. So whatever is the time, so earlier time was 0, so now we are going to insert the time plus 1. Okay, fine. So now we have inserted 6 10 1. Okay, and now the loop will run again while queue. So is the queue empty? No, queue is not empty. Then we are going to pop 6. So now see, if we are going to pop 6, if we are going to pop 6, it will okay, in the node 6 and time is 1, time has 1. Now it is checking the neighbor of 6. Now it's checking the neighbor of 6. Now it is again checking. Now it is again checking 3. We are unnecessary will go into the loop, because 3 we already checked. Now for the 6 it is again checking 3. So we need one set where we mark the node as a visited. So we need one set we need one set where we node mark as listed. So as soon as we put into the queue, we will mark the node as a listed. So in starting, we put start node, so we will mark as a listed. Listed dot add start. Now we will append the neighbor. We will mark as a listed. Listed dot add neighbor. Okay, listed dot add neighbor. So now six. Uh, Visitor dot add neighbor, and before appending, okay, so we are adding the neighbor, but before appending we will check if neighbor not invested, then only we are going to do this. Okay, so basically what we are doing is, so first we insert 3. First we insert 3, 1 minute. First we insert 3. So we will mark as a 3 as a visited. Okay, so visited as 3. Now 6, 10, 1. Right. So we are running a loop on 6. So is neighbor is 6. We are running a loop. 3 is 1, 10, 6. Right. So let's suppose 1. Okay, 1. Is 1 in a visited? No, 1 is not yet visited. So we are inserting 1 and increasing the time by 1, and we are marking 1 as a visited. Okay, then 10. Then this 10. This 10. This 10. Then is 10 is in visited? No. Is 10 is a visited? No. Then we are going to insert and we are mark it as a visited. So we are going to mark as a visited. Now 6 is in a visited? No. Then we are going to mark as a visited and we are going to insert into it, which is fine. Now we are going to pop. Now we are going to pop. Now 6 will be pop. 6 will be pop. So for the 6, it is going to check its neighbor. So for the 6, 1 minute, let me clear this. So what are the 6 neighbor? So we know for the sixth, the neighbor is 3. For the sixth, the neighbor is 3. Okay. So do we need to insert 3 again? No, definitely no. So that's why we put this check. If neighbor is not invested, but 3 is in the vested, because we are running a loop on this array 6 of 3. So neighbor is 3, but 3 is in the vested. 3 is already in the vested. So this will not even go inside. Okay, then again then we are removing 3, removing 10, sorry. So okay, now we are removing 10, then again neighbor is 3, again it will done. Now we are popping 1, so 1. So for 1 we are popping the 5, the neighbor is 5. Is 5 in the neighbor listed? No, 5 is not in the listed. Then we are going to insert 5, but by increasing the time plus 1. So here time is 1, then we are increasing the time plus 2. So we are inserting and we are mark as a listed. So this, then we are inserting 5 and 2. Then we are running a loop for this one, 5 for 1 and 4. These are the neighbors. So 1 is already in the listed. Yes, 1 is already in the listed. Then we will do the 4 and we will insert with by increasing 1 time, because whatever the time we are inserting 3. So 5 is the neighbor and 2 is the neighbor, but 5 already in the listed. 5 already in the listed, because as soon as we insert it into the queue, we are marking as a listed. So 4 and 3. Now we will pop 4, then we will append 9 and 2 with value 4, and then we are removing this as well. So at the end, what is the time? What is the time? 4. So the whatever the last time, so we have, that is the actual time. So let's try to return that time. Return time. So let's try to run it. Is it work fine or not? So our sample solution has been accepted. So let's try to submit it. So our solution has been accepted and we bid 47% and memory 77. So you can even, I think, like if you like we are using the queue, but if you use the DQ from collections import DQ, and here Q is equal to DQ and Q dot append. root, and here instead of pop left. Along with that, here I'll also use the DQ. I'm not sure whether it's going to increase our performance or not, but we are trying. Q dot append, and pop left. So let's try to submit it. So yes, it is definitely going to increase our performance. So even I read somewhere, so DQ has like more performance, right? So earlier we see we beat only 45% of the people, or 47. Now we beat 80% in the runtime. So you can use the DQ as well, like double-ended queue, right? Or either you can use the queue, but like both has, the approach is same. The approach is same, right? So the question is the medium category. So it's easy if we just know this thing, how we are going to traverse back. That's it. Because in the tree we can't traverse back, so we need to treat it as a graph, and for the graph we need to create the adjacency matrix. And how to create the adjacency matrix we already know. So after that the thing is very easy, and we know it's a like a tree, so definitely something we need to use the BFS and the DFS. So that we are doing already, right? So that's it. You can also try this question. I will provide the solution as well in my GitHub repo. And yeah, thank you.